Hi, my name is Mark Krasinovich. Welcome to Virtual Machine Preserving Host Updates for Zero-Day Patching in Public Cloud. The other researchers on this project are Naga Govindraju, Malur Raghuram, David Hepkin, Jamie Schwartz, and Arun Kishan, and we're all with Microsoft Corporation. In Azure, we have millions of servers running tens of millions of virtual machines. We periodically have to update the hypervisor, the host operating system, and the virtualization stacks on those servers to deploy reliability fixes, security updates, and roll out new features. One of the challenges that we face is that our update mechanism needs to be able to deal with zero-day fixes, those security urgent fixes that need to be deployed not in days or weeks, but within hours. We will also want to avoid full host operating system reboots that cause virtual machines to also reboot, because that causes major application downtime, also causes loss of cache state for applications, which is extremely disruptive. So our goal when we started out this work was to come up with an update mechanism for our fleet, where we could update millions of servers without rebooting virtual machines, and apply that mechanism for zero-day updates, where those updates would have to roll out across the fleet in hours and not days, as I mentioned. Back in 2012, we started working on virtual machine preserving host updates, or VM-PHU. The idea behind VM-PHU is fairly straightforward. The first step is to simply freeze the virtual machine state in memory, then soft reboot the operating system underneath those virtual machines, and then restore the state of those virtual machines and continue running them. The virtual machines in this case, instead of experiencing a shutdown followed by a restart, simply experience a small blackout time. And our goal is to, of course, minimize this period of blackout. We faced several challenges as we continued to develop this, as our fleet got more sophisticated. We have several types of hardware accelerated devices that virtual machines can use. One of them is our network adapter, which is accelerated using SROV. With these types of devices, we first, before the VM-PHU operation, fall back to a software shadow version of the network adapter. This causes a small brownout to the network performance of the virtual machine, followed by the blackout through VM-PHU. After the resume, we enable hardware acceleration and the network performance goes back to normal operation. The second type of accelerated devices we have are discrete device assignment devices, or DDA devices. These are devices that are directly attached to the virtual machine and so have no data path through the host. There's no software fallback, therefore. So we need to handle DMA and interrupt processing while the host operating system is being updated. The solution for this is to keep the IOMMU active during the soft reboot, maintaining the DMA and interrupt mappings across the reboot so that the devices are mapped to the same addresses into the virtual machine. So when the virtual machine's resumed after the soft reboot, we inject interrupts for each device that were missed while the hypervisor was online, and that causes the virtual machine not to lose any of its IOs. So let's go take a look at a rebootless update demo on a production server with GPU DDA VM on top of it, where we're going to update the Store VSP virtualization storage driver. Here I've got two remote desktop windows open. One of them on the right side is connected to a virtual machine running in Azure's infrastructure. That virtual machine you can see here in Device Manager has 4 NVIDIA GPUs connected to it in DDA mode. It's running a GPU-intensive 3D Mark benchmark, and I've got a script running on it that will detect blackouts caused by VM-PHU through clock drifts. On the left side, I've got an RDP connection to the host that virtual machine is running on. When I run the update command script, it's going to do a VM-PHU update of the store virtualization driver on that host. Pausing the VM for just 1 second, you can see, as detected by the blackout script. The 3D benchmark continues uninterrupted. Like I mentioned, one of the key goals is to reduce the blackout time caused by VM-PHU, which has 3 main contributions. One of them is the reboot time for the hypervisor and host operating system. Another is the time it takes to close virtual machine devices. And the third contribution is the memory preservation time. Let's take a look at each of these. The first, the time it takes to reboot the operating system is impacted by all of the I/O operations it takes to read the new kernel image and drivers and other components off of the storage medium. This can take tens of seconds on hard disks. So our solution in this case is to cache the reads and writes in memory and preserve them across a reboot. And this causes the reboot to actually occur from an in-RAM image. You can see the difference on the right, a logarithmic scale look at a normal reboot of the host operating system compared to a KSR soft reboot, which avoids the hardware reboot. And then finally, the KSR cache optimized reboot. You can see that the cache optimized reboots are below 10 seconds, even on hard disks SKUs where the host operating system is stored on a hard disk, whereas can be upwards of 100+ seconds in the normal reboot case. The second primary contribution is through the time it takes to close virtual machine devices. And in this case, if there's a straggler device, for example, a remote disaggregated disk that takes a long time to acknowledge the close operation as a virtual machine is being frozen and we're about to enter the blackout time, that wait for that straggling I/O causes blackout times for all virtual machines because we can't actually enter the soft reboot phase. So our solution here is to fast close the devices. What we do in that case is to serialize any in-flight IOs. IOs by definition are idempotent. So once we save them, after the soft reboot and we resume the virtual machine, we can restore the virtual machine and replay those serialized IOs. And we didn't incur any delays in closing those devices. We implemented this as a storage resiliency feature in Windows Server 2016. And then the final optimization that we made was to minimize the time it takes to preserve memory. The Windows Memory Manager, by default, uses linked lists for maintaining free regions of memory. So marking these pages as in use, which is required for the VM-PHU operation, is an order n squared operation, where n is the number of memory runs for the virtual machines. If virtual machines' memory has become very fragmented, this operation of marking those pages as in use can delay, again, the time that those virtual machines are sitting in blackout. In fact, we've seen cases where, on the right side, you can see blackout times of above 1,000 seconds when memory is extremely fragmented. So what we did was change the memory manager data structure to introduce an ON algorithm, which is based on a sorted list for the virtual machine memory runs. Using this approach, we are able to minimize the time it takes to preserve memory down into just a few seconds. Let's go take a look at a demo of a rebootful update on a production system running active VMs. Like before, I've got two remote desktop windows. On the right side, a connection to a virtual machine running on an Azure host. In that virtual machine, I'm going to start a download of a very large file, which will represent a running application in that virtual machine. I also have a script that is detecting VM-PHU blackout through clock drift. The remote desktop on the left side is connected to that Azure host that virtual machine is running on. And I'm going to run a script that's going to update the kernel image of that host. That update is going to proceed in several steps. In the first step, the kernel image is loaded into memory. That will take a few seconds. After that's complete, the virtual machine will be fast saved. At that point, VM will enter blackout period. The host will then kernel soft reboot into the new kernel image and then resume the virtual machine. When the kernel soft reboot starts, we're going to lose a connection to the host, and so the remote desktop window on the left side is going to close. We'll see at the same time a pause in the output of that application on the right. When the virtual machine is resumed, the script will print the blackout that was experienced. And you can see at that point, the application continues its download. We've been using VM-PHU in production since 2015. And at this point, we use it approximately 2 to 3 times per year to apply a rebootless update, and approximately 1 time a year for rebootful updates. The failure rates we achieve, which are largely due to hardware issues that are uncovered during the VM-PHU operation, is about 0.1%. And the graph shows the blackout times that we see across VMs for both rebootful and rebootless updates, where for rebootful updates, we see blackout times ranging anywhere between roughly 12 seconds up to about 20 seconds at the P100. And for rebootless updates, blackout times range from roughly 2 seconds up to about 9 seconds at the P100, with the average right around 5 seconds. VM-PHU has some limitations. It's designed for host operating system updates, like I mentioned. It can't be used for some of the other data center scenarios where we want to minimize impact to virtual machines, like for moving virtual machines off of hardware that we're going to decommission onto newer hardware, or dynamically load balancing virtual machines across server for better resource utilization or power efficiency across the data center, or to migrate virtual machines off of a server that is about to have an imminent hardware failure. For these types of operations, live migration is a better fit, and that's what we employ. There's also cases where applications can't tolerate the VM-PHU blackout pause. So for those types of applications, we send a scheduled maintenance event into the virtual machine roughly 15 minutes before the VM-PHU operation will take place. And that gives the applications in those virtual machines an opportunity to either fail away from the VM-PHU operation or prepare for it. And for customers that want full control over VM-PHU or opt out of it completely, we support that with our dedicated host offering. So in sum, VM-PHU represents a fast in-place update mechanism that we can apply universally for all updates, security, reliability, and feature updates across the entire Azure fleet, with no requirement for turn space. And importantly, it can serve as an update mechanism for zero-day updates that have to be deployed across the entire fleet within hours instead of days or weeks. We've applied it in production. We've achieved very low blackout times within the second range. And we continue to make optimizations to bring that blackout time down. If you have questions or feedback, feel free to contact me at markruss@microsoft.com or naga@microsoft.com.